Node3, dispatch D, January 2022, January 25th. This is from the Perimeter Institute and the coast of Quirks and Quarks, or Quarks and Quirks, not sure which. And this is the third and final part of the panel.
And so we'll just keep going anyway, even though we don't really know. Well, I'd like to open this up to our audience now. If you have questions for the panel, we have microphones on each aisle. And I invite you to come up to the front, and I'm going to ask that you only ask one question. And please make it a question, not a speech. And please say whether you want to direct to a particular panel member or the panel in general. So do we have any questions from the audience? Any questions from the audience? While we're waiting for the audience, I have one for the panel. Whenever you're talking about all this stuff about uncertainties and about maybe it's this, maybe it's that, what are the chances you're wrong? That everything we know is wrong.
I would say the chances are 100% that we're wrong about parts of some things. And I think it's probably close to 100% that we're not wrong about other things. And the problem is we don't know which.
That's good. Yes, sir, we have a question.
Hi. I guess I'll ask generally to the panel. Since we've been talking about information, I thought I would ask a question to try to clarify in my mind what information is. I think at one point we talked about information as being something physical that's described by physics, which led me to think if I had a notebook that I took my pen out and scribbled till my pen was empty, I had added some matter and some energy perhaps to the notebook. But then if I took that same notebook and wrote, let's say, prime numbers in it until my pen was empty, I feel like I added something different. What is that I just added in physical terms?
Hello. You know, it's for a very long time in human history, the idea of information had to do with meaning, right? Information was something that was about something, it meant something. And it seems to me you're trying to get at this distinction there. Now, one of the most remarkable advances in starting to build computers and to build communication systems like fiber optic cables was made by Claude Shannon at the mid part of the 20th century. He realized that you could talk about quantity of information and information being processed irrespective of the meaning of that information. So for instance, it's the cable guy's, his job is to come and get your house so that you can get, you know, a megabyte of information per second in there, and it doesn't matter if that megabyte is Shakespeare or if it's pornography, right? His job is to just get that megabyte in there. So now you're very rightly saying some information means a lot more than others. Not that, you know, there's a lot of useless and meaningless information out there. In fact, watching cable TV is a good way to find this. But it's actually very important for the theory of computation and information theory that you don't have to talk about meaning to talk about quantities of information and amounts of information processing.
But wasn't that also an example of the difference between the information which is in your mind and the carrier of that information, which is the paper?
Is that what you're trying to get at there? Sure.
Susskind, what do you think?
Well, I think that the difference is very real, and in some sense, the information in your mind is information about neurons, information about the particular configuration of your brain at an instant of time, and the information on a piece of paper is information about the ink drops on a piece of paper, and they're completely different bits of information. They may, however, be correlated. There may be connections between them, between those two different kinds of information. The correlations might be interesting. In a sane, coherent person, there'll be good, strong correlations between what's on the paper and what's on his brain. In a maniac, there may be no correlation whatever. So they are very different, they're different things, but they may be correlated to each each other.
But that correlation would be a thought. And yet, they think of it as a
The
thought.
correlation would be a physical correlation between one set of bits and another set of bits. A physical correlation in the physicist's sense of correlation.
Not sure what you mean. Because
Well,
he can leave the paper in his desk.
Correlation means that if you measure one thing, that influences what you would get if you measured another thing. So, if you come along with an experiment, a psychology experiment, and you write something down on a piece of paper, and somebody looks at that piece of paper, then you can do an experiment and ask what is the correlation between what's in the person's head. You ask him, what's on that piece of paper? I wrote down on that piece of paper that King Canute had warts on his nose. And now I ask somebody, what does that piece of paper say? And he says, King Canute had warts on it. Then the correlation has been faithfully established, but it's a correlation between two different collections of bits, not the same information. On the other hand, to show that it's not the same information, you can go take somebody who's insane and say, what does that piece of paper say? And he might say, Bob McDonald has bits on his nose. And therefore he got the correlation wrong. So,
Okay.
yeah.
Okay. Thank you very much. Question here.
Yeah, this is for Dr. Leonard Susskind or anybody else who cares to answer. One of the things that you said was that there's no evidence that there's a programmer or an outside source, mucking around with the laws of physics or the software of the universe, and or at least we haven't observed any. Now, this reminds me of like a video game. So
This is what?
reminds me of sort of a video game. Let's say your character's in a video game, right? And the player doesn't like the outcome and decides to reboot the game or reload it. And we as characters in the game, how would we ever possibly observe that somebody's mucking around with our system? So I'm curious, that raised the thought in my mind. How would you be able to observe such a change if it did occur?
No, I get the point. The point is well taken. That if you change the rules, start over again, how would anybody know that the rules were changed? One way you might notice that the rules were changed is that if you suddenly made a change, you might discover that history was inconsistent. That you come along and you suddenly change rules, and you might discover that what you thought were the oldest, most primitive dinosaur bones are found, instead of at the deepest level, they're found in the highest level of geological strata. Just because somebody came and changed some rules in midstream. And in that sense, you might find that what you thought were the laws of physics might not reflect themselves in what you would have ordinarily expected the historical record to reproduce.
Very good. Okay, thank you very much. Yes, sir.
My question is about if information can be without relation to any objective matter. Talking about information in our mind, there is a theory out there called autonomic brain theory from Carl Program, which tells that information exists as a spectrum inside your brain rather than attached to some exact neuron or something. So my question is, can information be present independent of a matter or... Yeah, that's my question.
Okay. Can the information just exist and then we sort of discover it? Is that the idea? Okay.
Yeah. No. No, Tony made the point in his early spiel on what he means by information, that information has to be about something. The very definition, information should be about something. Now, part of the discussion, we haven't quite gotten in that direction yet, but I think perhaps the most interesting thing to come out of the existence of the world being quantum mechanical rather than classical, is that we've discovered that the information is not what it used to be about. When one talked about the position, momentum of a particle and said one has information about it, one had information about what was actually there. In the quantum world, it seems that the information is not about what's actually there, but rather what comes about from an interaction. So people talk about these things called quantum measurements, and if one says a quantum state is information, Well, it's information about something, and that something is what will come about from the measurement interaction. So information is always about something. It's not just disembodied stuff out there like energy.
Thank you very much. Yes, sir, on this side.
Okay. So, my question is, if it is true that we cannot duplicate information or a system of information at the quantum level, isn't it meaningless to predict anything, since the process of prediction is to express something that we know and say that it's a duplication of reality, or is everything we know just approximations?
So there's actually, when the no cloning theorem of quantum mechanics says that you can't take a bit of information, a quantum bit of information, in an unknown state, and then make an exact copy of it. There's no procedure that will do that. But you can certainly take a bit that's in a known state and make a copy. Or even if you know if the bit, for instance, is electron spinning this way or spinning that way, you can create another electron that's spinning the same direction as the first electron. It's merely if the electron is in some unknown quantum superposition of being spinning up or spinning down, there's no procedure that will allow you to make a copy.
Yeah.
So you can certainly have deterministic behavior and make copies of certain types of information. You just can't go the whole hog and copy the whole quantum bit.
Yeah, let me say it a different way. You can't make a universal quantum cloner. You can't make a machine that will reproduce a configuration no matter what state it's in. But you can certainly make a machine, for example, that will reproduce up electrons or electrons at some particular location in space. So you can do repeated experiments to continuously reproduce electrons at the same point in space, but the machine that you make for that will not also be able to reproduce electrons which happen to be in with definite momentum. So you can't make a universal cloner. That's, I think, the right statement.
Maybe that's why there's only one universe. We just can't duplicate it, can we?
Yes,
Thank you very much. Yes, sir. Yes, sir.
This is for the panel in general about the hologram idea. Now, I know Dr. Susskind said you can't generalize the results from the black hole for the entire universe, but I just wanted some speculation on how the topology or the shape of the universe could, I guess, change its information content, or also if we believe that the universe is expanding, does that mean its surface area is expanding and it can hold more information in the future?
Yeah, I think the answer is yes, that it can hold more information because the surface area is expanding. But I will tell you this, let me just say it this way. This is one of the main questions that people like myself are struggling now and a little bit confused about. It is one of those questions that if I were to give almost any answer, the probability would be about 50% that I would be wrong. The application of the fundamental principles of quantum mechanics, the principles of quantum gravity and so forth, to the universe as a whole is really obscure, and we don't understand it. And it is perhaps one of the great and exciting facts of physics, that there's that much out there that we don't understand now. I don't have an answer for your question, a complete answer for it. But I would say, come to my seminar on Friday.
Which means you got a job for a while. We're almost out of time. We'll just take a couple more questions. Yes, sir.
I'm a biologist, so let's have a problem with semantics. If I go back to the bathtub analogy, the temperature, the motion, the energy of each of the molecules, to me is data. That's not information. It's when I take all of that together and decide whether I'm going to burn myself when I step into the bathtub. That to me is information.
Well,
How do you deal with the difference in that terminology between data and information?
Who would like to?
Anyone?
Well, I don't know. I think of data and information as largely being the same thing, as long as the data is about something. I think the physicist's use of data, now data doesn't mean data recorded in a notebook, it means data recorded in the molecules of the water in the bathtub. That data is what we do call information.
Perhaps our questioner is asking the difference between information and knowledge. There's information about that.
Information doesn't require the existence of anybody to know about it. You know, a tree that falls in the forest is a piece of information, It doesn't require anybody to know about it. The way physicists use information is a very impersonal, non-biological concept, which simply is, as I said, it's everything that specifies. I said everything you need to know, but let me say everything that in principle specifies what will happen next. And certainly we don't normally assume that somebody has to know what it is for it to be a piece of information.
Dr. Fuchs?
Oh, yeah, that was painful for me. Well, I spent a lot of time at Bell Labs, where Claude Shannon had come from, the man who invented information theory, and the way he worked out the concept, it was based on the idea of surprise. So a good experiment that I could do, for instance, is I could take this piece of paper and I could write a 0 on it. And I think in some of the perhaps loose talk we've been using here today, one would say, well, you've just written a bit on it. But watch this, I know he'll get the right answer. Seth, I'm gonna give you this piece of paper and it has a 0 on it. I give it to him.
Thank you,
Information
Chris.
is
Seth,
teleporting.
I'm giving you that piece of paper and it has a 0 on it. How much information did you gain from the paper itself?
None. It's got a 0 on it. I already knew it had a
He
0
already
on it.
knew that it had a 0 on it.
I would disagree. I would say he found out that there was a 0 on it.
No, he didn't. He
know
already
that.
knew it because I told him.
Actually,
He only knew that you said, with the information he had, was that you said there was a 0 on it. He did not know there was a 0 on it.
and in fact, come to think of it, since we go way back, I actually thought it was going to be a 1 until I
Nevertheless, what's the point of this example? The point of this example is, at least mathematically, the way information is quantified is in terms of the idea of surprise. And so if Seth has some ignorance about what I'm going to give him, then he looks at the thing written on the paper and he says, aha, I gained some information. But that's a function not only of what was on the paper, the actual physical configuration, but it was also a function of what he knew. So I just take a point with what Leonard said, that Leonard. I said Leonard. That in the background there is always this thing, maybe not a person, but someone who writes down probability and has some ignorance.
It's like the two fellows are looking at a flock of sheep, and one of them's a quantum mechanic, and the first fellow says, oh, those sheep have been sheared. And the quantum mechanic says, well, at least half of their sides have. Don't know about the other side, because I can't see. Okay. Yes, sir.
Following the postulate of the universe as a computer, do you know of any formalized study on what it might be working on?
Yeah, well, no, actually, so I think there is more of a reason. The simple fact that everything is processing information doesn't mean one shouldn't talk about things in terms of information processing, any more than the fact that everything's made out of superstrings means one shouldn't talk about superstrings, right? You actually get some very interesting predictions about the universe thinking about it as a computer. So one of them is actually you get a kind of a computational picture of the holographic principle, or analog of it, or it's complementary. So the holographic principle says, here's the maximum number of bits you can cram into some volume. That's proportional to the area of the volume. There's a computational version of that that says, what is the maximum number of ops or bit flips that I can cram into some time in a particular volume? And you find out, quite remarkably, that this is also related to an area. It's like the area of a two-dimensional world sheet that goes through the middle of this volume. And I guess the other thing, so I think that there are already in quantum gravity and black hole physics, ideas of information have proved very powerful, and the holographic principle is a particular example of this. But I think we can learn a lot about the universe by thinking of it as a computation. And the best thing about thinking about it as a computation is actually explain something which is quite mysterious. So, something that's very mysterious, at least from the physics perspective, is why is there so much meaningful information? in the universe? You know, why aren't we all just like a bunch of like random molecules bouncing around all over the place? Well, if you take something that's computing and it gets programmed at random, you can prove mathematically that it's likely to come up with all sorts of strange and complicated and fascinating patterns. Whereas if you just take the molecules of water in Lenny's bath and look at them, they'll just be jiggling around at random. So in fact, we learn something about why the universe is complex by thinking how it's computing.
And when it's done?
One last question. Yes, sir.
Well, the universe as a computer and a program seems quite interesting. But I have a question, like, if the laws of physics, have they changed since the beginning of time? Then that would affect, does that have any effect on the software? And also the completeness theorem, sort of like trying to define the entire sort of universe. You couldn't do that from within, as the computer program.
So that's an excellent question. So the laws of physics don't seem to have changed very much since the Big Bang, though they might be very different at other places in this very big universe of ours. But other kinds of scientific law have changed. For instance, the laws of biology are changing all the time, because the laws of biology are determined by the actual physical biological systems that are out there. And you brought up Gödel's incompleteness theorem. The way that applies to the universe as a whole, and actually you can derive this now by looking at the universe as a computer. One of the fascinating features about computation is that you can prove mathematically that if you have a computer and you set it off computing in some way with some program, and you ask almost any question about the far distant future of what that computer is going to do, the answer is you can't know. This is how this incompleteness theorem manifests itself in computers. It's called the halting problem. You can't even know if the computer is going to do anything a long time in the computer. In the future. So what this means for the universe as a whole is that we won't be able to predict the far distant future. The only way to find out what's going to happen is to let it happen and see what happens.
There's a wonderful short story written about the most powerful computer in the universe, and it was asked the ultimate question, is there a God? And the computer says, there is now. I'm afraid that's all the time we have for this evening, but I would like to thank our distinguished panel tonight. Dr. Chris Fuchs from the Leonard Institute, Dr. Tony Leggett, University of Illinois, University of Miami, Dr. Seth Lloyd from MIT, Dr. Leonard Susskind from Stanford University.
To learn more about the Institute and to enjoy other programs, visit us online at perimeterinstitute.ca.
Wow, that was incredible. I will try to tag everyone who was in that, and thank you very much to all the guests. Apparently that took place in 2008, which might explain why it's so hard to find a clean copy online.
Black hole.
Oh, there's more. Oh my.
And paradoxes that you find in quantum mechanics. Their research is also leading to new technologies to calculate, to store, to transmit information in quantum computing, quantum cryptography, and quantum teleportation. Beam me up, Scotty. So let's get down to the nitty-gritty.
Okay, I thought maybe it was an epilogue, but it's not. It's just like a loop back of the first 10 minutes or so. All right, I will, I gotta write another paper. This is Node3, the Night Watch Institute, signing off.